Hi everybody, welcome back. This is the last video on redox. It's Redox Lesson 6. And in this video we're going to talk about how chemical reactions can make energy. So how these redox reactions can actually generate energy. So a redox reaction in which the reaction happens spontaneously, because like a more active metal gives its electrons to a less active metal, right? The more active metal gets oxidized, the less active metal gets reduced. That's spontaneous. That'll happen without any outside energy. So when you have that kind of reaction, it will produce energy as long as you separate the substance that's being oxidized from the substance that's being reduced. And so all of these types of cells, which are referred to as voltaic cells or galvanic cells, we know as batteries. Okay, so this is how batteries work, how your cell phone battery works, how the batteries in your clicker work. This is how batteries work. So I know this reaction is not written in your notes. If you could write that reaction down, that'd be great. And we'll go ahead and identify who's being oxidized and who's being reduced. So we assign charges to anybody that doesn't have a charge. Remember, any element by themselves always has an oxidation state of 0. We can identify who's being oxidized by looking at whose charge is going up. And so the oxidation half reaction, in the oxidation part of this reaction, the Fe0 is turning into Fe plus 2. Since the charge is going up, the electrons are being lost, so we will write them on the right-hand side of the equation. And since the charge is going from 0, right, to 1 to 2, that's 2 places up the number line. We put 2 electrons on the side. So that's the oxidation half reaction. What we have is solid iron is turning into iron ions, aqueous iron. Okay? The reduction half reaction, because the charge is going down, is the copper plus 2 ion turning into solid copper, right? The no charge copper is solid copper. So we're actually making solid copper in this reaction, okay? Now, we're going down the number line, right, from plus 2 to 0. So 2 electrons are being gained to go down the number line. Now, if the iron, if these two species were in direct contact with one another, nothing would happen. But if we separate them and put iron in one cell, these are half cells. If we put iron over here, okay, so this would be our solid iron. And as the reaction proceeded, it would lose electrons and it would turn into iron plus 2 in solution. If we separate that half cell where oxidation is occurring, and it doesn't always have to be on the right, I just drew it that way, from the half cell over here, where reduction is occurring, and if you look at the reduction half reaction, we already wrote it out down there, there are copper ions in the solution, right? Think of this like liquid, okay? There are copper ions in the solution, and that is turning into solid copper. So this bar represents the solid metal. So there's copper ions turning into solid copper in that half cell. That's the reduction half cell, okay? So what we'd expect as this reaction proceeds is that this electrode, where the iron is turning into iron ions, this is going to lose mass, because the iron is turning into iron ions. So the amount of solid iron there is going to go down. Now the electrons that iron loses have to be gained by copper. So what we do is we force those electrons, this is our wire here, we force those electrons to be pulled by the copper through the wire into the solution. Okay, so those electrons are going to go into the solution. They're going to be gained by the copper plus 2, and that's going to turn it into solid copper. So electrons are moving this way from who's oxidized and who loses electrons to who's reduced and who gains electrons. Now copper, the solid copper, this is going to get bigger. This is going to gain mass. The substance reduced is going to gain mass because you're going to make more solid copper on that electrode. Okay? So this is the basic components of a battery, and we'll add some more things in just a minute. there are half cells. There is an oxidation half cell. And a reduction half cell. Okay, and they occur in separate parts. And we force electrons to move through a wire. So there is a wire that allows electrons to move. And they always move from the oxidation half from who loses them to who gains them. Okay? Now, we have names for these bars. These are called electrodes, and they have specific names. So this would be the reduction electrode, and this would be the oxidation electrode. And the electrode where oxidation occurs, if you remember from your charts, anox, is known as the anode. So this guy right here is the actual anode. This actual physical solid metal, that's the anode. The anode is just the site where oxidation occurs. It's the electrode where oxidation occurs. And if you remember anox, red cat, what that means is that the cathode is the site of reduction. And electrons will always flow from the anode to the cathode, from who's oxidized to who's reduced, through the wire. They'll always flow through the wire. So this is your cathode over here. Okay? Now, if this were all that we had in terms of our battery, it would work for about a millisecond, and then it would stop. Because as the negative charge moved this way and this cell became more positive, it would track the electrons. And as this cell became more negative, it would repel the electrons. So the electrons would stop flowing. So we need something to neutralize the charge in the half cells, and that's the job of the salt bridge. It keeps the cells neutral by allowing movement of ions. And a salt bridge can be anything made of salt, anything made of a plus minus and a plus ion and a minus ion. You could use a hot dog or a pickle as your salt bridge. Okay, but a salt bridge would be added here, and you're going to have to add the salt bridge into your half cells, something like this. Okay, and in that salt bridge, I'm just going to erase this little arrow for the electron movement. I'll write the electron movement up here. So if negative electrons are moving to the left, then negative ions would move to the right. Oh, except I made it a positive. What's wrong with me? Okay, and positive ions would flow the other way. Positive ions would flow in the same direction as the electrons. So the salt bridge keeps the cells neutral, and it allows ions to move. Okay, that's really important. Ions move in the salt bridge, and electrons move in the wire. Okay, the wire is for electrons. And that is the basic component of any battery. And eventually, you'll either run out of iron, right? You'll either run out of this, right? Or you'll run out of this, and then your battery goes dead. And if it's rechargeable, then you could force electrons to go the other way, so you could force the reverse reaction to happen, which would regenerate what you need to make the forward reaction happen. But as this reaction proceeds, it produces energy, and that is the energy that our batteries provide. Okay? Oh, one other thing I should mention here is the charge of the electrodes. The anodes in a battery in a galvanic or voltaic cell, since the anode is the source of electrons, it is the negative electrode, and the cathode, just like a cation, is the positive electrode. So when you see on a battery, you know your little batteries, I'm really bad at drawing, but pretend this is a battery. This is your plus, and you got the little indent down here, and that's your minus. This is your cathode, that's the site of reduction up there, and this is your anode, that's the site of oxidation. Okay? And those two cells are separated by a wire, and as the electrons move, they generate electricity. Okay? So there are other, oops, I think it's here. There are other, I have to pause this. Okay, I'm back. The other type of electrochemical cell is known as an electrolytic cell. So the one that I just diagrammed was called voltaic or galvanic. The other type is electrolytic. And electrolytic cells require energy. And they require energy to make a chemical reaction happen. So like recharging your batteries, right? That's an example of an electrolytic cell. And you have to be able to compare and contrast them. When electricity is used to force a chemical reaction to happen, the process is known as, you have a blank in your notes, it's called electrolysis. So we learned like let's say NaCl plus Cu. Now copper is lower, so it wouldn't normally be able to kick sodium out of a compound. But if you supply energy, you can make it happen. So this reaction is not spontaneous, but you can make it happen by adding energy. And if you add energy to this, the process of making that happen is called electrolysis. So we would electrolyze the solution, which would allow the copper to kick out the sodium to make sodium and copper chloride. But again, that's an energy requiring process. It forces a non-spontaneous reaction to happen. So you have 10 things on your Venn diagram here. What you're probably going to want to do is, I'm just going to draw it, it's going to be less confusing. You're going to want to complete your Venn diagram so that you have circles. On this side, you're going to have voltaic cell, which is your battery. On this side, it's mislabeled in your notes. You'll put electrolytic cell. And obviously, in the middle are things that are true of both. So number one is anode is the site of oxidation. Cathode is the site of reduction. Anox, red cat, is always true. So those, that goes for both of them. Number one and number two go for both of them. In a voltaic cell and in an electrolytic cell, anox, red cat is always true. Number three says electrons flow from the wire from the anode to the cathode. That's also true. Okay? Electrons always go from anode to cathode. It doesn't matter what kind of cell you have. Okay? So number three belongs in the middle too. Number four says a redox reaction occurs spontaneously. That's in a voltaic cell. Number five, a redox reaction is not spontaneous. That's an electrolytic cell. The anode is positive. That is one thing that's different. In an electrolytic cell, the anode is positive. So that's only true in an electrolytic cell. As we drew in the voltaic cell, the anode was negative. Okay, another difference then is the charge of the cathode. In a voltaic cell, the cathode is positive. And in an electrolytic cell, the cathode is negative. Bye, guys. Okay, so one thing that's different is that the reaction is spontaneous here. The reaction is not spontaneous here. Okay, that's one difference. Another difference is the sign of the anode and cathode. Okay, that's it. Everything else is the same. So they both involve redox reactions. The anode is always the site of oxidation. The cathode is always the site of reduction. And electrons always flow from A to C, from anode to cathode. Electrons flow in alphabetical order. That's it for this unit, everybody. Remember, we'll have our test on Wednesday of next week. Enjoy the rest of your weekend. Remember, don't leave your valuables in your car. Bye-bye.